All right, Chapter 11, Section 5, Alternating Series. So in this section, we're going to learn how we can deal with series whose terms are not necessarily positive. Up to now, everything we've dealt with has been series whose terms are all positive. So here's our first opportunity to deal with something where that's not true. So we're going to be looking at cases where they alternate. Positive, negative, positive, negative, positive, negative, right? As the name implies, alternating series. So an alternating series is a series whose terms are alternately positive and negative. So here is a couple of classic examples. So we have a case of 1 minus a half plus a third minus a fourth plus a fifth minus a sixth, and so on and so forth, right? So this one has a very famous name. This is a harmonic series, right? So harmonic is just the one that harmonic is the one where they're all positives. 1, 1/2, 1/3, 1/4, going down. So a harmonic series is the series 1 over n, as n goes from 1 to infinity. So they're all positive. So 1, then a half, then a third, then a fourth, then a fifth, and so on and so forth. And remember that this is a series that very famously does not converge, right? This does not add up to some constant. This adds up to infinity. It just keeps growing, 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 growing. So this is one of those famous examples of a series whose individual terms are all positive, whose individual terms converge to 0, and yet the whole series diverges. Okay, but here we have almost a harmonic series. This is the alternating harmonic series. So here we have 1, then minus a half, plus a third, minus a fourth, and so on and so forth. So this is how we write it down. It's going to be negative 1 to the power of n minus 1. So this little exponent up here determines the alternating series, right? In some cases, for some choices of n, we'll end up with an even exponential power, which means that all of this turns into a positive. And for some values of n, this exponent is an odd value, which means that this stays negative. And so it alternates between positive, negative, so on and so forth, right? The other way we can establish something that alternates is to have the exponent just go to the power of n, right? So both of these two things accomplish the same goal of alternating signs between positive and negative. It's just a matter of whether you want to start with a positive and then a negative and then a positive, or whether you want to start with a negative and then a positive, then a positive and a negative, and so on and so forth. So these two things accomplish the same goal. You just have to be careful about the details, right? So here, n starts with 1, so the whole thing will start off with a positive, and then a negative, and then a positive, and then a negative. Whereas here, because it goes to the power of n, it starts off with a negative, right? The first term is negative, then positive, then negative, then positive, and so on and so forth. Okay, so here are two classic examples of alternating series, and we want to determine if these series converge or diverge. We see from these examples that the nth term of the alternating series is of this form. So what we can do is take the series and strip it away into sort of two pieces. The part that changes signs, right, times the part that doesn't change signs. So when we rewrite it this way, the b sub n is positive, right? It's the positive component of the term, right? And we can either write it this way or that way. So the following test says that if the terms of the alternating series are decreasing towards 0 in absolute value, then the series converges. Okay, so the alternating series test states that if we're given a series that alternates in this way, then if we can establish that the sequence is decreasing, right? This is how we describe that the individual terms are decreasing, right? Remember that as we write these down, b sub 1 minus b sub 2 plus b sub 3 minus dot, 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 dot. Eventually, we get to b sub n, and then the one after it, right? And it could be plus or minus depending on, how this thing is, how it starts, where it ends. But the one right next to it is going to be b sub n plus 1, the one right next to it. So this is indicating that the one after it is smaller than or equal to. So this is notation that it is decreasing or equal to. And this is indicating that the individual terms are convergent towards 0, right? So if both of these are satisfied, then the series is convergent, right? That's what the alternating series test is giving us. Okay, so I'm not going to go through a formal proof, but let's just kind of think about why this would be true, sort of conceptually, and then we'll move on to some examples. So to show that this is true, let's think about the sequence of partial sums. So remember, the partial sums, s sub 1, is just going to be equal to the sum of the first one. That's just going to be 1. And then s sub 2, the second partial sum, will be b1 minus b2. Right? And then the third partial sum is going to be b1, minus b2 plus b3. And then s sub 4 is going to be b1 minus b2 plus b3 minus b4. S sub 5 is going to be b1 minus b2 plus b3 minus b4 plus b sub 5, right? Okay, and so this is where these two conditions have been satisfied, right? So we're given some sort of sequence. It's alternating, so we know that we have b sub 1 minus b sub 2 plus b sub 3 minus b sub 4 plus b sub 5, dot, forever, right? So we're looking at the sequence of partial sums. And both of these things have been satisfied. So that means we know that the individual values stripped away from their sign. So all the b sub n's are all positive. It's just a matter of whether we're adding them or subtracting them. But all the b sub n's are positive. So b sub n so b sub n is greater than or equal to 0. Right, so they're all positives. Okay, so visually, let's see, we have a number line. Oh, okay, so without loss of generality, let's just start with 0 there, just to kind of visually see this guy. Okay, so here's 0. I'm gonna do or look at visually graph what it would look like to go a distance of b1 in this direction, right? So b1 is positive, so that means that right there, this is going to be s sub 1, where this is the distance b sub 1, right? And so there's s sub 1. And then the next one, well, it's got to be b sub 2 is positive, so s sub 2 is going to go in the opposite direction. So I'm going to start from here. I'm going to start from here and then go in the other direction. Now, it cannot go past it in this way because these two conditions have been satisfied, and so the next one has to be smaller than b sub 1. So b sub 2 has to be smaller than b sub 1. So I can't go out that far. So it's going to go back somewhere, but not all the way back to 0, right? So it's got to be somewhere in between here. So let's just say that it's somewhere around there. So this is where s sub 2 would lie. S sub 2 would lie somewhere around there. Okay, but then now the next one, we would add a value. So this time we got to go back in the opposite direction. And so now we would add a b sub 3. Oh, let's put the fact that in this direction we're doing a minus b sub 2. And now we're going to add a b sub 3. So we're going to go over in the other direction. Now again, b sub 3 has to be smaller than b sub 2, so we can't go like that. It can't be longer than b sub 2. It's got to be smaller than it, right? So again, without loss of generality, I don't know, it's just maybe somewhere around there. Say somewhere around there. So that would be where S sub 3 lies. Good. And then we move on, and then the next one would have to be S sub 4, and again, we have to go in the opposite direction, and we can't go all the way back, so we've got to go somewhere, say around there. Oh, so this would be plus B sub 3, and now we want to go minus B sub 4, and then it would end somewhere around there. There's S sub 4. And so you can see that as we move forward with this and extend this process out, the next time we would go this way, and then the time after that we would go back this way, and then the time after that we'll go back this way, and so on and so forth, until eventually we're going to land somewhere, right? So it's going to converge to something, given that both of these conditions are satisfied. So hopefully I've convinced you in some general way that this has some merit. Let's look at an example. So example number 1, let's look at the alternating harmonic series, right? A very famous series. Again, let me refresh your memory that the harmonic series which goes from 1 to infinity of 1 over n, which is 1 plus 1/2 plus 1/3 plus 1/4 plus dot 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 dot, diverges. Right? It's a very famous series that diverges. And this is the example we use to show that just because the sequence values converge to 0 is not good enough. It's necessary but not sufficient to prove that a series converges. In other words, if you show that a series is not going to 0, then you've shown that it does not converge. However, if you've shown that a series does go to 0, your job is not done yet. Right? You haven't shown that it necessarily converges. You've just shown step 1 of something that's important toward it, but it might not be enough. Okay, so that's a very famous series. It diverges. Let's work with this one, though. Okay, so it's going to have alternating values. So we can change this alternating series into the following, or separate it this way. 1 to infinity of -1 to the n minus 1 power over n is the same thing as just having -1 to the n minus 1 times 1 over n, right? And so we've separated this way. So here's the alternating part, and this part here is what we consider that b sub n, right? Note that b sub n is always positive, right? It's the positive component of this. We're just adding the plus and minus, plus and minus. And so all we have to do is show that it satisfies both conditions, and if it does, then we can conclude by the alternating series test that it is going to converge. Okay, so the first thing we need to show is that it's decreasing, right? To show that it's decreasing, we need to show, number 1, that b sub n plus 1 is less than or equal to b sub n, that they're smaller to each other. There's a couple ways to do that. Number 1, you could just show that, hey, it's always true for, remember, n is these positive values, that n plus 1 is always greater than n for these values, right? This is for n equal to 1, 3, 4, dot, 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 dot. For positive counting numbers, it's always true that n plus 1 is bigger than n. Well, then I guess we can just throw in that n plus 1 greater than or equal to n. That's just for free, right? Because that's always true. And so now when we flip it underneath a fraction, since they're always positive, keep that in mind, then 1 over n plus 1, it's got to be less than or equal to 1 over n. And so the first one has been satisfied. Good. That's one way to do it. So the other way to think about this, right, that's option 1. Option 2 would be to think about the fact that consider the continuous function f of x equals to 1 over x, right? In this case, the continuous function, it's true that f of n equals to 1 over n, right? So if we take this continuous function and we plug in the counting numbers, then we get back to that one. Good. And so now we can show that the derivative d dx of 1 over x is equal to d dx of x to the negative 1 power, which is equal to negative 1 over x squared, right? So it's always negative. So if the derivative is negative, then we've shown that the function is decreasing. Okay, all right, so, and so that's part one. Part two is to show that the limit is converging to 0. The limit as n goes to infinity of 1 over n equals to 0, and so that one's pretty obvious, right? So we've shown that both conditions are satisfied. Yes, that's true. And we've also shown that this is also true. So by the alternating series test, we've shown that the alternating harmonic series converges. So we've shown this is true. We've shown that's true. So by the alternating series test, the alternating harmonic series converges. Let's see what your author did. Okay, so before we move on, I want to introduce a couple of interesting sequences that I think highlight something important about the alternating series test. So bear with me. Let's consider the following sequences. So right now I'm just identifying the sequence, not adding them yet, right? So say that the given sequence is described this way. Let's say W sub n is equal to 1 over n squared whenever, this is for n equal to odd, and that's equal to 0 for n equal to even. Okay. So then let's write down the first few values in this sequence, like this. So when n equals to 1, 2, 3, 4, 5, here's the first 6 values in this sequence. So for all the even ones, the sequence is just going to be 0. So that's 0 there, 0 there, 0 there. That's easy. And then for all the odd ones, then we follow these instructions. So 1 over 1 squared, that's just going to be 1. 1 over 3 squared, that's going to be 1/9. 1 over 5 squared, that's going to be 1 over 25. And so on and so forth. Good. Okay, so now also I want to introduce another kind of a kooky sequence over here. Let's consider y sub n described as 1 over n squared, again for n equal to odd, and then 1 over n for n equal to an even one. Again, let's write down the first few values of this sequence. So 1, 2, 3. Okay, so when n is an odd number, it's 1 over n squared, so that'll be 1, 1/9, 1 over 25, and let's throw in one more, 1 over 49. When n is even, we follow these instructions. So this one's just going to be 1/2, 1/2, 1/4, 1/6, and so on and so forth. Okay, so here are the two sequences. Now let's consider the series made up of these. So let's say that we have this series. So this is a sequence. So now the series from n goes from 1 to infinity of -1 to the n-1 power of w sub n. Right, so now it's a summation. So it's going to be adding these things but taking turns. And the way I've written it here, the very first one, when n equals to 1, we get 1 minus 1, which is 0. Anything to the 0 power is 1. So the first one's going to be positive. When n is 2, 2 minus 1 is 1. -1 to the power of 1 is negative. So this is going to be 1 minus 0 plus 1/9 minus 0 plus 1/25 minus 0 plus ... forever, right? That's what we're interested in. And then over here, let's consider this other series as n goes from 1 to infinity of -1 to the power of n y sub n, right? So here I've raised to the power of n instead of n to the -1 power. All that does is change the order in which we start adding and subtracting, but it still gives you the same added effect of alternating signs, right? So this one is the same thing as, okay, when n is equal to 1, we have a negative, so this would be -1 plus 1/2 minus 1/9 plus 1/4 minus 1/25 plus 1/6 minus 1/49 plus ... forever, right? Okay, so our goal is to figure out, do these converge, do these diverge, and what about how does this connect to the alternating series test? Okay, so it's the alternating series. So let's consider the conditions for the alternating series test. So let's take a look at those one more time. Okay, so here was the statement for the alternating series test, right? We had this sequence, alternating values, and then as long as both of these two conditions were satisfied, we were able to conclude that the series was convergent. Okay, so let's explore these two things for for the two series that I created. One is that they're decreasing, and two is that the limit as n goes to infinity of the individual terms, the absolute value of the terms, or the positive terms, that limit equals 0. So let's explore both of these. Okay, so the fact that the limit equals to 0, let's do that one first. Well, okay, that doesn't matter. Okay, so number one is that they're decreasing, right? So decreasing. That's what this notation of b sub n plus 1 less than or equal to b sub n, monotonically decreasing. We want to show that. Now, how do we show that here? Well, that's easy. They don't decrease. We can just see it right here. Notice the sequence values. They decrease here, but then they increase. But then they decrease. But then they increase. But then they decrease. Right? So it's not true that for any value in my sequence that the one right next to it is going to be smaller. Right? So this fails. I don't really need to do anything. It's just obvious. And same thing over here. For this series, we see that it is decreasing to begin with. Sure. From 1 to 1/2, it does decrease. And then from 1/2 to 1/9, it is also decreasing. But then from 1/9 to 1/4, it increases. and then it decreases, and then it increases, and then it decreases, and so on and so forth. So again, it's pretty obvious that it fails. Decreasing, in other words, the b sub n plus 1 less than or equal to b sub n. This one also fails that. Fails. It's not monotonically decreasing. Okay, so then what about the second condition? The second condition was that the limit as n goes to infinity of the w sub n, that it equals to 0. And that's going to be true, right? That's because whenever it's odd, we follow this rule, and that clearly shows that it's going to 0. And whenever it's even, it follows this rule, and both of them equal to 0, so the limit will go to 0. What about this one? Well, same thing. We have a sequence defined by the evens and odds. So the limit as n goes to infinity of y sub n, well, it's going to be equal to the part where that goes even, that's going to go to 0. The part where it goes odd, that's going to go to 0. So I think it's pretty clear that they both go to 0. Therefore, the limit does exist and it converges to 0. So that part is good, right? It doesn't fail that. It passes that part of the test, the conditions. That condition has been satisfied. In both cases, this condition has failed. But now let's look at the actual series. Does it converge or does it diverge? All right, so let's look at this one first. Does it converge? Does it diverge? Okay, so let me ask you to think about the following. So we have that the series n goes from 1 to infinity of negative 1 to the n minus 1 of w sub n, that this equals to 1 minus 0 plus 1/9 minus 0 plus 1/25 minus 0 plus dot, 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 dot. And we want to know, does that converge, does that diverge? I think it's pretty easy to convince people that whatever this sum is going to be less than or equal to the following sum. 1, keep the positives, 1/9 plus 1/25 plus, right, keep all the positives, and then all of the minus zeros, right, the minus 0 isn't really doing anything, so I can easily replace it with 1/4, right, and then this one replace it with 1/16, good, and then this one replace it with 1/49, oh, sorry, 36, 36. And what we have here is the following. This thing is equal to, this is equal to the sum as n goes from 1 to infinity of 1 over n squared. And we know this converges. Converges by the p-series test, right, with p equal to 2. And since this is a subset of that, right, all we're doing is replacing all these blue ones with a minus 0. That's not going to affect it. So if this giant infinite sum going forever converges to some constant value, then certainly this one also converges, right? So hopefully I've convinced you that this series converges. Okay, what about this other one? All right, so now we have this sum as n goes from 1 to infinity of negative 1 to the power of n y sub n, which is going to be equal to negative 1 plus 1/2 minus 1/9 plus 1/4 minus 1/25 plus 1/6 minus 1/49. So on and so forth, so on and so forth. Okay, so does this converge, does this diverge? All right, let's try and separate these in the following way. Let's put all the pluses together. This is going to be equal to 1/2 plus 1/4 plus 1/6 plus dot forever. And then let's put the minuses together. This is going to be minus 1 minus 1/9 minus 1/25 minus 1/49, and so on and so forth, so on and so forth. Okay, they all have a minus. Keep that in mind. Okay, so what is this guy? These are all the even ones, right? So what we could do is we could factor out a 1/2 from all of them. So if we factor out a 1/2 from all of them, then it's 1/2 times all of this. And now this is a harmonic. This diverges. Right? This is a harmonic. Diverges. Times 1/2, still infinity. Infinity times 1/2 is still infinity. So the whole thing here is just going to be like some sort of infinity value. And then we have this minus all of these negatives. So I can factor out a -1. -1 times, and then make them all positive. 1 plus 1/9 plus 1/25 plus 1/49 plus dot. Okay. Well, this looks an awful lot like the n squared one. So we could say that this is definitely less than this part here is similar to what we just did on the other side. It's the same thing as 1 plus 0 plus 1/9 plus 0 plus 1/25, right? Adding extra zeros in the middle there doesn't really do anything. Plus 0 plus 1/49. Right? So adding zeros doesn't do anything. And if we replace all those zeros with a positive number, 1/4 and 1/16 for that one. So we end up with 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 plus 1/36 plus 1/49 dot. Okay, so I've changed it. I did add something, but it must be true that this guy is definitely a little bit bigger than that one, right? This is a subset of that one. And this one converges, again, by a p-series. This is the same thing as the sum of 1/n squared as n goes from 1 to infinity, right? 1, 2, right? The denominators are all the counting numbers squared. So it's this one, converges. So this one converges because it's a p-series with p equal to 2 to some constant, and this is a subset of that. So it's also got to converge. So this one converges to some constant, to some constant, right? This one converges to some constant, and this is just a subset of that one, so it must also converge. Good. Okay. And so what we end up with is, going back to here, we separate this into the positive and the minus, the pluses and the minuses, and all the pluses just add up to infinity. And then we're going to subtract some constant from here. Well, infinity minus a constant is still going to be infinity. So what we've established is that this series diverges. Right? Diverges. Okay, so what's the point here? We have two different sequences. Here, let me put all this together in a table so we can see what my point was with all of this. Okay, so we had these two sequences, and then we determined that both of them failed to be monotonically decreasing. So fail, fail. But both of them were successful in that they were converging to zero. So successful, successful for this part here. Success, success. But then when we come back and look at the actual convergence, it does converge. So success here converges, but fails over here. Fails to converge. Fails to converge. My point being that I think it's very common that that students show that the individual sequence converges to zero, and then they kind of skip this part here, and they just assume this implies that, and therefore that that the sequence converges, the series converges, and we can see that that's not true by this example. So here we have an example, two separate sequences, where in both cases the limit goes to zero. In both cases, it fails to be monotonically decreasing. Yet in one case, it does the series does converge, and in another case, the series doesn't converge. Okay, so when you're applying the alternating sequence test, make sure. My point is to make sure that you satisfy both conditions. That the limit as n goes to infinity, b sub n goes to zero, and also show that it is monotonically decreasing. All right, let's look at some examples from the book. Okay, so here are the exercises from chapter 11, section 5. Let's take a look at a couple of these. When we start with, say, something like number 8, we have negative 1 to the power of n times n squared over n squared plus n plus 1. So let's take a look at that. Okay, so the sum as n goes from 1 to infinity of negative 1 to the n power times n squared over n squared plus bn plus 1. Okay, so note that this can be thought of as our bn, b sub n. Right, this is our b sub n. And note that b sub n is always positive for n equal to 1, 2, 3, dot, 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 dot. Okay, we can also write down the first few values of this list. Okay, so when n equals to 1, we're going to start off with a minus. When n equals to 1, we'll end up with a 1 in the numerator, and a 1 plus 1 plus 1, which will be 1/3. Then plus, and then when n equals to 2, we'll end up with a 4 in the numerator, and we'll end up with a 4 plus 2, because it's 6, 7, minus the third one, that would be a 9 in the numerator, and then that'll be a 9 plus 3, makes it 12, 13 in the denominator, plus so on and so forth, so on and so forth. Okay, so we have the first couple of values in there. We have a sense of what it looks like. So let's apply our test. Okay, to determine whether this thing converges or diverges using the alternate series test, we have two things we have to think about. Number one, we have to show that it is monotonically decreasing. We have to show that b sub n plus 1 is always less than or equal to b sub n, decreasing. That's number one. And number two, we have to show that the limit as n goes to infinity of the b sub n equals to 0. This one is usually, well, often one of them is easier to show than the other. And you don't have to prove, or if you can show that one of them fails, then you're done. The alternate series test is going to fail to show that something converges or diverges, right? So let's look at this thing, number two. So the limit as n goes to infinity of n squared over n squared plus n plus 1, well, clearly that's going to be equal to the limit as n goes to infinity of, and let's multiply the numerator and denominator by 1 over n squared over 1 over n squared. That'll give us a 1 divided by a 1 plus 1 over n plus 1 over n squared. And so we see that each one of these is going to go to 0, 0. So this whole limit is going to be equal to 1. Because the limit equals 1 and not 0, as is required by the alternate series test, it already fails this criteria. Fails. So in fact, you don't even have to worry about this one, which might be a little harder, right? So whenever you're looking at an example, you need to show both of them are true. So go for the easy pickings. Pick if one of them is, if it's easier to show that one of them is going to fail, go for that one, and you don't have to worry about the other one. Otherwise, you might have to take a derivative of this ugly thing to show that it is decreasing or not decreasing. But in this case, that's an overkill because we've already shown that this part fails. So it's not going to work out by the alternating series test. Now, strictly speaking, that doesn't really allow you to conclude that it converges or diverges. At this point, we're just saying the alternate series test isn't really going to give us a valid conclusion. But, however, if we go back and look at the test for divergence, it must be true that the individual terms of the series must go to 0. So this fails to converge by the test for divergence. Right? So my conclusion is going to be so this series diverges by the test for divergence, right? So that, remember, the test for divergence was just that the individual terms must converge towards 0. If that fails, as it did here, then there's no chance that the infinite sum can add up to a constant. It will add up to infinity because we keep adding things that are, in order for us to even begin to have a chance of the whole summation to infinity adding up to anything, the individual terms must be going to 0. Okay, let's look at another one. How about number 12? Okay, so the first thing I would like to do is rewrite this a little bit and write it as n goes from 1 to infinity of negative 1 to the n plus 1 times n over e to the n instead of n times e to the negative n. Either one, right? So these two things equal each other. So this part here is our b sub n. And for us, right, it's greater than 0. It's always positive. This is for n equal to 1, 2, 3, 4, dot, 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 dot. Obviously, the numerator is always going to be positive, and the denominator is always positive as well. Right? Think about the graph of e to the x power. E to the n power is just a subset of that, or individual dots in that sequence. Right? If we had the graph e to the x, then e to the n is just going to be the individual values where n equals to 1, and then n equals to 2, and so on and so forth. That's what this denominator is going to be, always positive. So the whole thing is always positive. Okay, again, we need to show two things in order to use the alternate sequence test. Number one, we need to show that it's decreasing, monotonically decreasing. In other words, a b sub n plus 1 is less than or equal to b sub n. Okay, in order to do that, let's take a derivative, right? So let's consider the continuous function f of x equals to x over e to the x. Its derivative, well, that's going to be low d high minus high d low over the denominator, squared we go, the quotient rule, right? Which then we can factor out an e to the x from the numerator, and then cancel out one of these guys to give us 1 minus x over e to the x. And again, as established before, this part is always positive, and this, the numerator, will be positive, positive for x greater than 1, right? Okay, so now keeping in mind that f of n, plugging in the counting values instead of an x and n, f of n is equal to n over e to the n. In other words, it's a subset of that. We've established that it must be true that these are decreasing. So we've established that our sequence is decreasing. Okay. For n strictly greater than 1. So for n equals to 2 or 3 or 4, we've shown it's decreasing. Okay, the other condition is that we have to show that the limit goes to 0. Number 2, the limit as n goes to infinity of that b sub n value must be equal to 0. So for us, that's the limit as n goes to infinity of n over e to the n. Well, that's just going to be a case of infinity over infinity. So we can use L'Hopital's rule. We can L'Hopital it and say that this is equivalent to the limit as n goes to infinity of the derivative of the numerator, that's going to be 1, over the derivative of the denominator, that's going to be e to the n. And now that equals to 0. So we've shown both that it is decreasing as well as shown that the limit equals to 0. So by the alternating series test, we can conclude that our series does converge. So the series n times e to the negative n as n goes from 1 to infinity converges. Okay, let's take a look at, say, something like number 14. Alternating values of arctangent of n as n goes from 1 to infinity. Remember that if you just remember the graph of arctan, then this one should be easy to figure out. So let's Okay, so to answer this question, I just want to refresh your memory on the graphs of these things. So remember that if we have x, y, and we want to graph tangent, then tangent looks like this. It'll come this way and come back this way, go through 0 and go that way. And that's when this is positive pi over 2, and this one is negative pi over 2 over here. Okay, so now if we want to do arctangent, then the graph looks like this, where we have an asymptote this way at positive pi over 2, and another asymptote over here at negative pi over 2. And the graph will come this way and then go down to 0 and then go down that way and approach that way. Good. So this is the graph of tan inverse. Tangent inverse of the input. We usually like to stick with x as our input and now our output. Oh, that looks confusing, huh? So let's stick to changing this back up to y as the input, and now we have an x. So this is x and y over here. Okay, so now if we have individual values of n, this is for n equals to 1, then we have a little value there, and n equals to 2, we have a little value there, and so on and so forth. So we can see that the limit as n goes to infinity of arc tan of n, which is the same thing as the limit as n goes to infinity of tangent inverse of n, we can see that it is heading toward pi over 2, which is not equal to 0. It already fails that condition that the limit as n goes to infinity of b sub n must be 0. And so by the divergence test, we can see that this sequence is going to diverge. So this guy here, my conclusion is that it diverges by the test for divergence. Right? The individual terms of the series must converge towards 0. If that doesn't happen, then you can already conclude that the whole thing is not going to go to 0. How about 16? That one's a weird one. N cosine n pi. All right, so let's think about the graph of cosine. Remember, the graph of cosine looks like this. Starts there, comes back down, comes back up, comes back down, comes back up, and so on and so forth. And it just so happens that all of these key values here, we have 0. And then right here, where it hits -1, that one is pi. And then right there, when it goes back up to +1, that one is 2 pi. And then this one down here, that's going to be 3 pi. Okay, so the cosine function hits +1 and -1 as multiples of pi. Good. So this guy, when n equals to 1, will be pi. That's going to be -1. When n equals to 2, it'll be 2 pi. 2 pi is +1. So this thing is just going to alternate between positives and negatives. So we can say that that thing is equal to -1 to the power of n, right? Because we start off with negative first, and then the n over 2 to the n. Good. Okay, and so now looking at it that way, this can be my b sub n. B sub n is positive. And now all I have to do is show that it satisfies the two conditions for the alternating series test. Number one, I want to show that b sub n plus 1 is less than or equal to b sub n, that it's decreasing. Okay, so to show that this thing is decreasing, we can take a derivative and show that the derivative is negative. Again, we go over to consider the continuous function f of x equals to x over 2 to the x power, right? Here, we can note that f of n equals to n over 2 to the n. So if we take this continuous function and then we input the counting numbers, right? If we input into here the numbers 1 or 2 or 3, dot, 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 we're going to get this, which is the sequence of interest. So the one we're interested in is a subset of that. Right, if we graph it, this will be a continuous function, and then individual little dots will represent the values we're interested in. Okay, so now if we take the derivative of this guy, f prime of x is going to be equal to Again, we can use the quotient rule. It would be low d high minus high d low over the denominator squared we go. So we had seen this one before, 2 to the x, 1 minus x, all over 2 to the x squared. And now one of these guys can cancel for that and that. So this is always positive. Always positive. And then this one is always positive as long as x is strictly greater than 1. So it works out well for us as long as it's bigger than that. So we've concluded that this sequence is going to be decreasing. Right? So we've established that n over 2 to the n is decreasing for n equal to 2, then 3, and 4, and 5, and blah, 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 blah. Okay, so we got the decreasing part. Now we just got to show that the limit as n goes to infinity will go to 0. The limit as n goes to infinity of b sub n equals 0. So for us, that's the limit as n goes to infinity of n over 2 to the n. And we can L'Hopital rule this. And so that'll be equal to 1 over, and then the derivative of this is equal to 2 to the n ln of 2. And so the whole thing equals to 0. Okay, so we've established both conditions are true, this one and that one. So we've established by the alternating series test that the series we're interested in is going to converge. So the series as n goes from 1 to infinity of n cosine of n pi over 2 to the n converges by the alternating series test. Is anything else interesting? How about number 18? It's going to be an easy one. Okay, so chapter 11, section 5, number 18. We have the sum as n goes from 1 to infinity of -1 to the nth power cosine of pi over n. Again, so let's think about the graph of cosine. So cosine starts at 1, comes back down, goes back up, comes back down, and so on and so forth. Cosine of x. X, and here we go. Okay, so when n equals to 1, we end up with cosine of pi over 1, which is cosine of pi, which is going to be right here. Right, here is pi. So we'll end up with -1 as that first value. When n equals to 2, we end up with cosine of pi over 2. Well, that's just going to be this guy right over here, pi over 2. Okay. When n equals to 3, we'll end up with cosine of pi over 3. And so that'll be over here somewhere. Okay, so my point is that as n goes to infinity, cosine of pi over n is going to approach cosine of 0, right? The pi over n is getting closer and closer and closer to 0, so that this, remember these are values on our cosine, it's going to be values that are getting closer and closer and closer to 1. Okay, so applying the alternate series test, we see that this part can serve as our b sub n, true, and except for the first term, we are going to have values that are positive, right? They're positive values, except for the first one. So it's greater than 0 for n strictly greater than 1. In fact, did they? Yeah, they did. Okay, that's fine. However, as we've just established, the limit as n goes to infinity of b sub n, which is equal to the limit as n goes to infinity of cosine of pi over n, is going to be equal to 1. It's not going to be equal to 0. So my conclusion is going to be that this diverges by the test for divergence. Right? The individual terms are not going towards 0. So the limit as n goes from 1 to infinity, negative 1 to the nth power cosine of pi over n, diverges by the test for divergence. Okay, that should be enough to get you started on your homework.